Ladies and gentlemen, with a huge round of applause, can we welcome Mr. Satinder Singh, Director of Solution Architects at AWS India and South Asia. Welcome, sir. Thank you very much.
If it was not for this esteemed guest, I had one song in my mind, which is from my favorite singer called Vanessa Williams, which says, "Save the best for the last." So with that, look, I think I've been in this conference since the beginning. And one of the things that I've taken away is the need to build models. Build more models, large models, small models, domain-specific models. And there have been various approaches that have been talked about by esteemed panelists and some speakers. I'm going to talk about things that we are thinking about from an AWS standpoint in this domain. You know, this is an area of active interest to us. We've been deeply thinking about how do we solve some of the engineering challenges so that model builders like you can build at scale and at speed. Before I get into this is a chart that perhaps every model builder would have encountered when they were building the first model. This chart is from a groundbreaking paper that was released in 2020, which is called Scaling Laws. What this paper hypothesized was that if you increase number of parameters, amount of data, and amount of compute, the models are going to become smarter and smarter. And we have seen this in action. Now, I'll not hazard a guess whether this law will continue or it's going to plateau as Moore's law has. But you know, there is something fundamental as you examine this graph. This graph is not a linear graph. It's a log-log graph. Straight lines on log-log graph can be fairly misleading. As an example, if you just see this compute graph, it shows loss and amount of compute that is required to reduce the loss. And just if it is not very clear, in order to halve the loss, you require 1 million times more compute. I repeat, just to halve the loss, to make models smarter, 1 million times more compute. Now think of this. This was done in 2020. I understand compute is becoming larger and larger and smarter. But this is the problem of today. And that's why billions of dollars of investment is going in building the right kind of infrastructure for artificial intelligence. Let me quickly talk about how at AWS we are thinking about it and some of the engineering challenges that we are solving. The first one is we need to build the most powerful AI server possible. Traditionally, as opposed to other applications, AI inferencing and training is not very amenable to scale out. And I'll detail that as I further through my discussion. So we need to build more and more powerful servers. The second one is, even if they build most powerful servers, it is still not going to be sufficient given the training and inferencing requirements of these models. So we need to scale out, but we need to scale out very, very efficiently. Let's first talk about scale up. And you know, there was a discussion just before this talk from the panel on GPUs versus CPUs versus something else, processing units, by the way. We truly believe that we need to provide customers choice of the right tool for the right job. And what you see on your screens is basically range of instances that we provide to our customers so they can build the right kind of training workloads, and they can also host right kind of inferencing workloads. Series of GPUs as well as CPUs. But the thing that I wanted to draw your attention, which is going to be part of the next 5 minutes or so, is this Trainium chipset. And let me put a context behind this. We are known as a world's largest cloud service provider. But I think what is not known so publicly about us is we build our own chips. We build our own chips, and we build it at scale. The first example of that is Every EC2 instance, which is every compute instance that you have ever used on AWS, contains a piece of hardware, which is a Nitro hypervisor, which is a hypervisor on the hardware, plus it does security and other things as well. There are additional benefits. Every EC2 instance has that chipset. We built it from ground up. The second one is on CPU side. I don't know how many have heard of Graviton, which is our own purpose-built CPUs. Again, at scale. Last year, we publicly reported that 50% of CPUs deployed in AWS regions across the world in last 2 years have been on Graviton. So that's the scale that we've been operating on. And we are bringing that scale and intelligence to the world of artificial intelligence as well through this chipset called Trainium. Let me quickly talk about what Trainium is. Let me start with the architectural concept. And the professor was talking about computer architecture, so there are students. It happened to be my week subject as well. More on that if you want to have an offline chat. I almost missed the job that I wanted to land from my campus because I flunked there, at least in the interview. But more on that offline. The traditional GPUs have been built on an architecture where there are multiple processing engines. And you pack in a lot of density, a lot of cores into GPUs because what they excel at doing is they do the same set of operation on different types of data. That's what GPUs fundamentally do. It's a groundbreaking architecture, has excelled many workloads, including AI. And then that's why you see demands for GPUs going up as you're thinking about large and large models. But when we were thinking of creating an AI accelerator, we decided to take a different approach. Our approach was based on systolic arrays. What systolic arrays do is essentially, think of it as large computing pipeline. So that one processing engine forwards the computed task to another processing engine. So it's a long processing cycle. It gives one unique advantage, that for every time we do an operation, there is no write or read from memory. Right? We optimize systolic array architecture into an array, which is optimized for matrix multiplication as well as tensor. That allowed us to create a matrix of multiple processing engines doing the task. And that got us tremendous amount of efficiency. I'll detail that as I go further. Now, this is an example or a picture of Trainium 2 chipset. Two chipsets, what you see on both on the small boxes on the left and right are HBMs, high bandwidth memory. For the first time, I'm also creating a cross-section of this. So we sliced it along the lines that you see, and it's enhanced through microscope. And what you clearly see are few engineering-related things that we've been able to achieve. The first one is these chips are not connected through a PCB-based motherboard. These are through interposer. And that gives us 10x more throughput as compared to the motherboard-based connections that are there. These are connected using small dots that you can see, which have been magnified, but they're 100 microns. And then you see on the bottom, power wires, which is delivering power. And I'll detail that also as I move forward. So very advanced packaging techniques have been used to build Trainium 2. The results are there on your screen. As compared to any comparable EC2 instance, including on GPUs, Trainium reduces the cost of training by almost half. I repeat, again half. 30 to 40% better price performance combination as compared to GPU-based instances. Not stopping there. The second challenge that we faced was power, delivering power efficiently. And this challenge has been spoken by multiple panelists before me. How do we make it more and more efficient? Because the power requirements are enormous. Our first series of Trainium 1 instances were based on, okay, before I explain that, let's take a step back. What happens for anyone who's studied chip manufacturer or understands chip architecture, would understand that you need to deliver voltage, lower voltage when finally the charge is going to go to the computer, to the processor. In order to do that, you need to lower the voltage just before it hits the processor. But it is more efficient to deliver power at a higher voltage to reduce losses. Our first Trainium 1 architecture, and what you can see on the screen, which is highlighted, is delivering these voltage regulators, which were fairly close to the processing units. With Trainium 2, we have taken a notch further. And what you see here is these are step-down transformers right there at the back or the bottom of the motherboard that allowed us to create shorter wires to deliver the same voltage. And that had resulted in 3x lower power per teraflop as compared to our previous generation instances. 30% lesser, again, as compared to any GPU-based instances on AWS. That's a massive power saving. These are some of the examples. Leading model builders like Anthropic, Poolside, who have been developing models for code generation, have been using Trainium to reduce their cost of training. Now let's move on. The second thing that we have done is exposed via Trainium what we call as neuron kernel interface, giving direct access to the chipset to make things run faster and faster. An example of that is, I don't know, it may not be very visible from the back. This is a profiler, kernel profiler, that Anthropic built using NKI to profile performance and debug all the systolic arrays that I talked about. Getting a deep insight into what's happening, where there are stalls. That dramatically improves performance. And to developers, it gives tremendous amount of visibility that otherwise is not possible. Let's move on. We are not stopping at Trainium 2. We have already announced our plans to deliver Trainium 3. This is going to have 2x more compute, and it's going to be based on 3 nanometer technology. It is expected to be out soon. Let's move on. As I said, even if they build the fastest servers, fastest chipset, it's still not fast enough. So we looked at 2 additional approaches. The first one is we built a neuron link, a chip-to-chip interconnect with direct access to memory at 1 microsecond latency. That's an interconnect built for Trainium. What it has essentially allowed us to do is build something that we call as ultra server, which can combine 4 such Trainium 2 servers and deliver almost 80 petaflops of compute. But we are not stopping there either. Let's look at dimension of scale out. And one of the things that you need to understand when you're scaling out, which practically would be a reality if you're running a large training job, is it's just not compute. It's just not HBM. It's just not all the cool things that I've talked about. It will fundamentally come down to networking. Right? If you think of networking, and you think about networks have been fairly, I'll say, demanding things. And you look at traditional networks versus AI networks, everything remains the same. It's just that AI networks are more demanding. They are more susceptible to failure. They need better latency. They require higher throughput. Everything that traditional network does, AI network demands more of it. We recognize this and created internally what we call as 10P 10U network. What it means is this network will deliver 10 petabits of throughput at less than 10 microsecond latency. I repeat, 10 petabits at less than 10 microsecond latency. It's an enormous thing. Imagine doing that in conventional data center, it's going to take years to do that. Then the next thing is, when you're training, then there would be a lot of interconnected compute instances. That creates a very complicated scaled network topology. The topology does introduce few challenges as well. The first one is, what kind of an architecture would you like to have? The first one is, think of it as a centralized architecture, like a master-slave, wherein there are advantages because you can centralize, but there are disadvantages too. At scale, it just fails. The second approach that industry has taken is look at decentralized architecture. Highly available, no single point of failure. So it eliminates all the disadvantages which is there in centralized architecture, but one big disadvantage, which if anything fails, then the time to recalibrate is enormous. And for AI workloads, that's expensive. All the protocols, network protocols that you've seen, OSPF, BGP, are based on decentralized architecture. But it is, again, not sufficient for AI workloads, especially when you're training. So we created another architecture called SIDR. Purposefully so that network people can remember it. You can call it SIDR, but it's just that instead of a C, it is S. What SIDR allows you to do is basically, in case of any failure, the reconvergence time is less than 1 second, which is 10x faster than any protocol, most efficient protocol for decentralized implementations. Now, to bring this thing together, there have been some scaled implementations that I can refer to. Project SIBA, which is a supercluster that NVIDIA uses internally for their R&D purpose, is based on AWS and all the technology that I talked about. The second scaled implementation that I can refer is Project Rainier, which is the largest supercomputer that Anthropic has built, 5x larger than the previous built supercomputer. Again, based on all the technology that I talked about, including Trainium. Now, we do understand I've talked a great deal about some of the things that we're doing that people do not know or don't associate typically with AWS. So how do we bring it all together for you? So instead of going and talking about use this technology, can we bring this all together in an easy-to-consume fashion, remove undifferentiated heavy lifting for model builders so that you can go and just focus your energies on building powerful or more efficient models is through SageMaker Hyperpod. I won't have time to get into details of it, but there are libraries, there are technologies that are used, the things that I've talked about, and in an easy-to-use fashion that you can just leverage SageMaker Hyperpod and leave all the undifferentiated heavy lifting to the platform. These are some of the, for more tech-centric folks, these are some of the frameworks and infrastructure that it supports. The moot point being that it doesn't tie you to any specific framework or technology. I repeat, not any specific framework or technology, because there was a lot of discussion today in this conference about being open. SageMaker Hyperpod lets you remain open. These are some of the scaled implementations of SageMaker Hyperpod. Hugging Face, Perplexity. They've been using SageMaker to improve their training times and reduce the undifferentiated heavy lifting in experimentation and building models. With that, thank you for your time. And as we say, I'm just going to close out with one thought. The thought is what our founder says, Jeff Bezos. And he says, innovation comes in various shapes and forms. And he believed that the most powerful innovation is the one that allows others to innovate. We truly believe in that. So we are providing you tools and technologies so that you can reinvent and innovate. Thank you.